Okay, everyone, we're getting started. This is CSCE 313. My name is Jason Bakos. Normally, I have about half of you have taken the companion course to this 611, but I don't see a lot of. Hold up. Syllabus. Don't see too many familiar faces, so it looks like most of you are taking this class first. That's good. I think it's a preferred way, preferred but not enforced ordering. So we've changed up the way we're going to run this course this semester. It used to be 2 75-minute class times per week, and then we would arbitrarily split those between lecture and lab time. This semester we've changed it to where we will have one weekly lecture on Mondays at this time for an hour and 40 minutes, and then there'll be a weekly lab section for the same amount of time on Tuesday, Wednesday, or Thursday, depending on which section you registered for. It looks like the Wednesday lab session has by far the most enrolled students, which is not optimal. I was hoping to have it like divided in thirds, but it looks like the way that everyone's schedule was, we ended up with the most enrollment in the Wednesday section. So if you're in the Wednesday section and you find it to be a little crowded and you have availability during the Tuesday or Thursday lab session, please feel free to go to one of the other ones. There you go. Does that make sense? You guys with me? Okay. So generally we're going to, this is a lab-based course. So we're going to spend the lectures kind of introducing each lab and then and in some cases giving a little extra help on the labs. And then in the lab session you'll be able to sit with a partner and work on the labs. Okay, you guys with me? Okay. So let's see. I have some dates on there. First lecture is today. Last lecture is April 29th. We'll have a final exam on, I believe it's May 6th, from 4 to 6:30. But if you look at the final exam schedule, it doesn't actually have a entry for this time. It's kind of a non-traditional. There you go. This is a non-traditional meeting time, and it doesn't match up with anything that's on the final exam schedule. So if any of you have a conflict during that final exam time, let me know. If you have another final exam that conflicts, you shouldn't, but in case you do, let me know. Unfortunately, we have a holiday next week on Monday, so that's going to complicate things a bit. I'm not sure if I'm going to get far enough in this lecture for us to get started in the lab this week. So we may end up skipping the first week of lab, but we'll see how far I get. The lecture is in this room, and the lab is going to be down the street in Swearingen, and it will initially be in 1D49 on the first floor, but sometime during the semester we are going to change the lab room to 3D22. The department has, actually I should say the college has invested a pretty good amount of money in building the lab on the third floor out, and we're turning it into a nice computer engineering lab. We're going to have not only computers, but we'll have lab benches and test equipment up there, soldering stations and that kind of stuff, but it's not quite done yet. So we're going to start off in 1D49, which I'm not thrilled about because there's no projector, so we have no ability to lecture in there at all. But at some point we'll move to 3D22, and obviously I'll let you know when that will be. Okay. The textbook for the class is this one, and it is optional. If you happen to get it, there's just additional information in there, but I'm going to give you everything you need in class. The prerequisites for this class are officially it's 211 and 212, which is digital logic design and computer architecture. Hopefully all of you have taken 240, which you should have because that's a 200 level class and this is a 300 level class. Because in this class, we assume that you are familiar with C++ and Linux. If you're not, you may need some help with some things, and I'll be happy to help you myself and the TAs. But we assume in general that you're comfortable with C++ and Linux. We're actually going to be using C in this class, which is just a subset of C++. I've got the bulletin description on there and my contact information. I'm in this building on the second floor in room 2213. I've got my phone number and office hours on there. And we'll have 3 teaching assistants for this class. The first one is Rasha Karachi, and she has her office in my research lab upstairs on the second floor as well in 2236. She has office hours on Tuesday, and then she will be running, her and James Coleman over there, that's James. Rasha and James will be running the Wednesday lab session. Okay, so they'll be walking around and answering questions. And then Rasha also has the office hours from 9:30 to 11 on Tuesday. And then James is an undergraduate teaching assistant. He's taken this class previously. And he will also be in the Wednesday lab session. So I have 2 TAs in the Wednesday one because it's the most students. We have 28 students in Wednesday. And then we have a third teaching assistant, Dallin Williams, who will be covering the Tuesday and Thursday labs because those are both tiny. I think we've got 7 and 8 students in Tuesday and Thursday labs. So those are small. Now, if the lab sessions somehow become rebalanced throughout the semester, then we may have to change things. But currently, that's how we have it set up. Two TAs in Wednesday and 1 TA each in Tuesday and Thursday. I use the departmental Moodle Dropbox.csc.sc.edu. I think you're all familiar with that by now. I put the schedule, downloads, announcements, labs, grades, lab submissions, miscellaneous material, announcements, and I record all my lectures and I'll put a link to the lecture videos on there as well. I have a YouTube channel and I'll put both the audio and my slides for all the lectures. So if you miss a lecture, you can just go there and watch it. Or if you need to, and I think in this class especially that'll be useful because during the lecture I'll be doing some tutorials with the tools. Hopefully I'll get through one today. So that'll be a place that you can go back and check if you have trouble with the software we're going to be using. And go back and watch the video. We're going to be using licensed electronic design automation software, EDA software, in this class, which is installed in all the departmental labs. So currently we've got 2 labs in 1D43 and 1D49 in Swearingen, and then as I mentioned, I think the plan is to move the computers from 1D49 to the 3rd floor lab once it's done. So we'll always just have 2 labs. One of them will be 1D43 and the other one will be 1D49, and then it'll transition to 3D22. So the software is available in there. If you want to install the software on your personal PC, let me know and I can help you with that. You can do it. It's just a really big download. Yeah, and you have to download it from the Intel's website. It's like 25 gig download. But if you want to have it on your own system, that's fine. You could also remotely access it as well. Yes.
So that software we need Linux to run.
Yeah, well, it runs in Windows and Linux. Actually, when I don't have a Linux laptop, so I'll be doing the demos on my Windows machine here. But the user interface is the same, so it looks the same both ways. We're also using these. We'll be using these project boards. These are FPGA embedded development boards. It's called the DE2 115. You're going to be working in groups of 2, And these labs will be available, these boards will be available in the lab for you to use while you're there. You can do some design and writing code without the board, but generally speaking, if you want to test your code, you need to have a board. So you'll have to be in the lab. I think there's a way we can simulate some of the components on the board. We haven't ever gotten that to work yet, but that's one of the things I'm going to try to get working this semester. But no promises. Typically in the past you have to have the board to deploy your software. And I'll talk more about that in a little while. And I also want to note that all the announcements that I post on Dropbox are sent out over email to your university email at email.sc.edu, so make sure you're checking that or forwarding that. I use that quite a bit. Anytime there's some kind of bug that we find or some kind of something in the tools that's not working right, or a deadline extension, anything like that, I'll send an email out. Okay, then I've got the learning outcomes listed there from our official ABET syllabus. That's goal is to, we're going to be doing hardware-software co-design using a programmable embedded system, writing software that talks to hardware, and we're writing software that does real-time processing of audio and video data, just video data, and this never got the audio working. And we're using high-level synthesis tools to develop coprocessor architectures in an embedded environment. The grading structure is 80% of your grade is going to come from the labs, and then there's a final exam at the end that will be individual. All the lab grades will be, you and your partner will receive the same lab grade. Okay. The grading scale is posted on there. For those of you that took classes of mine in the past, this is a different grading scale than I normally use. But I've lowered the thresholds for the plus scores a little bit as compared to what I normally do, in case you've taken another class from me. There's an academic honesty policy. In this class, it's a little vague because you're working with your partner, so you and your partner are expected to contribute equally to the projects you do, and obviously you have to help each other and share code, share designs. When it comes to helping out other students in the lab, you're going to be working in a lab next to another group, and it's very often the case that there are some tips that you might pick up that you want to share with your colleagues in the class, or maybe they're getting a crash or they're having trouble with the tools. If it's related to the tools, the software, the CAD tools, the compilers, that stuff, you're more than welcome to help out other members in the class. But obviously you can't copy code or designs, right? And I think that should be fairly obvious, right? But I don't expect you not to talk to the other people in the lab. That would be silly. Let's see, attendance policy. Attendance in the lecture and the labs is optional, and as I mentioned, I'm posting my lectures online, so if you really wanted to, you could watch the lectures online and not come to lecture. The labs, if you finish your projects early, you don't have to stay for the whole lab. But it's more likely that you'll need more time to finish the projects than we give you, during the lab times, the 100-minute-a-week lab time. So you're probably going to end up being in the lab outside of class as well as during the lab. If you're there during the lab, the advantage of that is you get to ask questions to the TA that's on duty. Okay? In this class, as I mentioned, we do group work in here. Group size of 2 is preferred. If you want to work alone, you're welcome to do that as long as we have enough computers and boards to accommodate everyone. You could work alone. We don't. The labs are not enough work that you can't do it by yourself. The workload is enough for one person to do. So that's up to you. But I don't do groups of 3 because even with groups of 2, as you've probably experienced in previous classes, you'll never have a perfect sharing, of contribution, even in a group of two. There's always going to be one group member that's going to do more work than the other. When you have a group of three, that problem is even, in my experience, there's even been more imbalance. So ideally, we'd like to have groups of two. Start thinking about who you want to partner with. If you don't have anyone in mind, you need a partner, just send me an email, and I'll try to help you out. Late projects are charged a 10% grade penalty for each school day. When I say school day, days when the university is open and classes are in session, so generally Monday through Friday. For each school day after the due date, but the late penalty is capped at 30%. The reason for that is because the labs build on one another, so you can't skip a lab. You have to do them all, and you have to do them all in order. And the problem that we very often run into in this class is that if you get behind, then the problem sort of compounds, because if you get behind on one lab, then you're going to be behind on the subsequent labs, all right, unless you catch up. So we don't want we don't want one lab sinking, all the labs after it. So we cap the late penalty at 30%. And that 30% is relative to the score you receive on it. So you'll submit it, you'll get a raw score after we grade it, and then we apply the late penalty to that raw score. So I have an example on here. If you submit something 1 day late and you had an 80% on it, then your final score would be 10% less than 80%, which is 72%. Make sense, right? So there was we've done that different ways in the past, but that's from this point on, that's how we're going to calculate the late penalty. You can only submit one version, so don't submit one, and then you might submit something and you may get an 80, and then you're like, well, wait a minute, if I could correct it and submit it one day, resubmit it the next day, and possibly up my score from 80 to 90. No, we don't allow that. You can only submit one version of every project. If you have any disabilities, please contact the Office of Student Disability Services, and you can make arrangements for any kind of accommodations you need. Yes?
As far as submissions, does each person in the group need to submit it?
Just one. Yeah, when you choose your partner, you'll email me your partner name, and I'll set up a spreadsheet of the groups, and so only one member need to submit the project. But we'll put the grade in Dropbox under both members. Okay, and then the syllabus is a guideline subject to change. If we change it, we will let you know as early as we can. Specifically, what happens sometimes is we might not get to the 6th lab, depending on, a lot of times if we have closures because of weather, or if I'm at a conference, or if we get set back, then there's a decent chance that we will only get to lab 5. And as a result of that, we'll drop lab 6 and we have to re-weight the labs, okay? So that there's a pretty good chance that'll happen. I just want to let you know ahead of time. But if everything goes well, we'll get through all 6 labs, and that will be the grade weight of all of labs, okay? Okay. Also, the version of the syllabus I have on Dropbox is, in fact, this one here is a little bit more recent than the one I handed out. I just made a few tweaks to it, grammatical things, nothing substantive. Okay, I think that's it. Yep, that's all for the syllabus. Any questions? Any other questions? Okay, great. Okay. All right. So, what are embedded systems, and what is this class all about? An embedded system is a computer system that's designed for a specific purpose. And that's different from a general purpose computer system like a desktop computer or a server computer or even a tablet computer. Embedded systems are the ones that you find in some examples here: wearables, thermostats, space applications, automotive. There's a lot of crazy stuff going on in automotive now with these powerful computers they're putting in cars for driver assistance and self-driving. Drones, sensors, cameras, speakers, network equipment, those are all embedded systems. Embedded systems have specialized hardware. They only, if you're building a computer system to only do one thing, you only have to put the hardware in there that's needed to do that one thing, right? You don't have to try to make that system fast or efficient at doing any application. You only have to make it do the thing it's designed to do, right? Whereas a general purpose computer, they're designed for you to be able to change up the software on it, and they're supposed to be more generalized. So one of the differences you'll see is that in a general purpose computer, generally speaking, they are heavier weight. They're more powerful. And usually that comes in the form of them being able to run programs really fast by exploiting instruction level parallelism, by being able to fetch and execute multiple instructions at a time, and to execute instructions out of order as compared to how they appear in the program code, right? And they have big, complex cache systems, memory systems that perform well under a wide range of memory access patterns. And in general, with a general purpose computer, you don't necessarily have to think about how well your code will perform. You run the code on the computer and it'll run as fast as it could possibly run, because the processor is heavy weight enough to be able to extract performance, extract parallelism at runtime, to find parallelism, to find instructions that can be executed at the same time while it's running, right? The problem is that you pay a price for that. Those CPUs are power hungry and they're expensive, right? As compared to the tiny ones that you would have like in a wearable. You guys with me? So what I'm saying is that aside from algorithmic changes, aside from going to a different algorithm, like going from a bubble sort to a merge sort to speed up sorting, outside of that, when you write code in 145, 146, 240, you don't really think about, I have to write this code, I have to make this code efficient, right? You don't think about it because you just write the code and you're just worried whether it works or not. On an embedded system, a lot of times you have to spend time tuning your code to make it more efficient. You have to think about decisions you make when you write your code that affect its performance as well as its functionality, right? So this is the only class you'll take, the only programming class you'll take where we're going to be doing things to your code that doesn't actually change the behavior of the code at all. Like you'll go from lab 2 to lab 3 does exactly the same thing. The behavior of the code is the same. The only difference is we're doing things to speed it up, to make the code faster. So in this class, we're going to be doing performance optimization of code. Embedded CPUs are generally not reprogrammable, right? Usually not. Right? You can't go to your home router and run whatever code you want to run on it. Generally, the code is fixed. Sometimes the vendor will issue a firmware update or something that updates the code, but in general, there's only one piece of software that an embedded CPU will run. Embedded CPUs are also very lean and mean, and they're not powerful. They're slow compared to a general purpose CPU because they have a simplified structure in the sense that they're only single issue, one instruction per cycle, and they have simple caches. But the reason for that is that you can afford to do that because if you're designing a CPU and you know the code that's going to run on it, then you can just have the programmers write the code to run fast on that CPU. You can have the code be written specifically for that CPU, and you can still get good performance even though the CPU itself is not that powerful, for automatically trying to mine performance in code that's not tuned. You guys with me? Kind of hard to describe that, but the idea is that you have the programmers write the code at a low level, in a way that's aware of the underlying microarchitecture, right? So the code is not agnostic like most code that runs on a desktop or server is. The code is tuned for that specific architecture. And so that's the way you can still get performance out of a simplified and power efficient and cheap processor that you would have in an embedded system. And a lot of times, embedded CPUs don't even run an operating system. In fact, the one that we're using in this class will not run an operating system. Operating systems are designed for general purposeness. Operating systems provide services that are given to code, user code that you run on the CPU. They're used for multitasking, and they provide services to make the CPU as general purpose as possible. On an embedded CPU, you don't need that. You just run what's called bare metal code, meaning that you write code and you compile it, and it runs not on top of an operating system, but on top of just the bare CPU. And usually there's a thin layer under there called a hardware abstraction layer that provides some services, but not a full operating system. You guys with me? So what is you might be saying, well, what's the big deal? Who cares? What's the difference? The difference is that an operating system also protects you in a way, because if you write code, and you run it on, like when you're in 145, 146, if you wrote a program that does something bad, like tries to dereference memory address 0, for instance, it'll crash. And it's no big deal, because the operating system will kill it. It'll say seg fault, and okay, there's a bug I got to fix, right? If you're writing bare metal code, though, there's nothing to crash. There's no. If your code crashes, the whole system just bricks when you don't have an operating system. There's no recovering from that. Usually, you have to re-download the code or reflash the processor. So writing code, it's kind of a catch-22, because in an embedded system, you're writing very low-level code. You're writing it in low-level C code, right? You don't have a lot of layers of abstraction, library support, that kind of thing, or an operating system. But on the other hand, it's also dangerous, because if you make a mistake writing low-level code, which you're apt to do, there's not a lot of help for you in terms of there's no cushion. It just crashes everything. It's hard to diagnose problems sometimes. So that's something that you kind of have to get used to when you write code for embedded systems. Do you have a question?
I forgot.
Okay, sorry. Now the other thing about embedded systems is that I mentioned that I'm saying embedded system because in an embedded system, it's not just the CPU that's specialized for a given task. It's all the hardware, all the memory. There's a special memory. There's a special peripherals and I/O devices. These days, they tend to make these instead of having a system board with the CPU and all the peripherals on it. Nowadays, because of Moore's law has allowed us to put so many transistors on one chip, nowadays they use these system-on-chip designs where basically they create one chip with the CPU and all the peripherals on one chip. So that way, the whole system is one chip, and it's much cheaper to manufacture. If you crack open an iPhone, it's one chip, one chip in the memory. There's not a lot of discrete components on there, right? And so here's a picture of, this is actually an Apple A9. So there's a CPU here, right? But you can see that the CPU only occupies about, 20%, 15% of the surface area of the chip. All of this other stuff is GPUs and coprocessors and, of course, radio, the radio for the modems and the LTE modem and the Wi-Fi and Bluetooth and all the I/O devices, I/O memory controllers, USB controllers, all that kind of stuff. They bring that all into one chip. So what you end up with is a CPU that is the master of the system, and there's all these peripherals that act as slaves. And the CPU is what runs everything. It runs the show, it runs it sort of coordinates everything. But in terms of the whole real estate of the chip, it's actually a small part of it, right? All the peripherals are on chip. So when you write code for embedded systems, you often have to write code for this guy that talks to the other components on here, and the communication is done through a network on chip or some sort of on-chip interconnect. And in this class, we're going to be using one called Avalon, which is the language, the protocol that the CPU talks to these other chips on. So you have all these peripherals, and they all have this Avalon interface. And anything that has an Avalon interface speaks one common language that can communicate within this system on chip. Right, a couple other things. I skipped this slide. So a couple other contextual things here. If you compare, this is a programming class, but we also add hardware design. There's some elements of hardware design in here too. So I call it software, hardware co-design. But if you compare this class to your other programming classes like 240 and 274, we are going to be writing, we're writing code in C, as I mentioned. And one of the other big differences that you need to be aware of is we are going to develop the code on a desktop computer. So you use a desktop computer to write your code and to design the hardware and to do all the compiling. When you're done, you push a button or you type a command, and you're going to be taking that compiled code and that compiled design, and it's going to be offloaded to this board, right? So you are writing code and you're cross-compiling it for a different technology other than the one that you're writing the code on. And then when you run it, you're running it on here. Okay, now there's a JTAG cable which is used for debugging, right? So you can monitor things on your desktop computer, but you're going to be writing code on one machine and running it on another, right? That's kind of crazy. This is the only class you'll get to do that. But that kind of workflow is becoming increasingly common, right? Because we've got all these consumer electronic devices all over the place. And so, like, you know, when you write code that runs a digital camera, obviously you can't compile your code on the digital camera. You compile it on a regular computer, and then once it's compiled, you offload that code onto the digital camera device, the platform, and you run it and test it on there. You guys with me? So it adds a layer of complexity to the programming process that you guys are not going to be used to at first, because it's already frustrating enough trying to write code and run it on your desktop computer, but it can be more frustrating and confusing sometimes when you're writing it on one computer and then executing it on a totally different machine. And this is this thing is unlike any other computer. And I'll get to that, more details on that in just a minute. I think I covered everything else here. Right. So, also in this class, a lot of what we do in this class is write code and try to boost its performance. There's a lot of that. That's kind of the theme of this class. You know, you write code, you design hardware, some hardware, you run code, you write C code that runs on that hardware, and then we do tweaks to try to make it faster. So that's a lot of what we'll be doing in this class. The question is what code do we care if it's faster? How much code do we write where it's important for it to be faster? And as you guys might guess, a lot of that has to do with graphics, right? That's why everyone, like when a new video game comes out, you have to buy a new graphics card, right? Because you want the graphics to be faster, you want the frame rate to be higher, you want there to be more pixels and more colors. It's all about performance when it comes to graphics. So in this class, we focus on graphical code. We write code that does graphics, and we try to design things that make it faster, increase the frame rate, essentially. The graphical code that we write is very simple. We start out with taking an image and transforming it by rotating it, right? And we do that for several labs, and then towards the end of the semester, we'll do a fractal code that generates a fractal, which is kind of a computer-generated graphic. But in both cases, our goal is to try to make it go faster. And we explore both software and hardware approaches for that. You guys with me? So, you know, hardware is we increase the number of cores we have on our chip. And then for the software, we do things like go from fixed point to floating point to fixed point and try to speed things up. And then we also are going to be using some methods to evaluate the performance of the code. So performance counters and measuring the dynamic instruction count, right? So that kind of stuff. Okay, so how do we do that? How are we designing hardware, first of all? How's that work? Because we can't like make a chip, right? The way we do it is we use a device called a Field Programmable Gate Array, FPGA. An FPGA is something that probably none of you have heard of. Very few people have heard of FPGAs. It's not a very commonly known term. But it turns out that FPGAs are in lots of things that we use every day. We just don't know it. An FPGA is a chip that can be electronically programmed to behave as any digital logic circuit we want. So you design hardware, you design a hardware circuit, and then you compile that into a net list, and you use that net list, a bit stream to reconfigure the FPGA to behave like that circuit. So you could think of it like an FPGA is a chip that when you first power it on, it's nothing. It doesn't do anything. It's a blank slate. It's just a paperweight when you power it up until you send a bit stream into it, which configures it to morph into an arbitrary digital logic circuit. Now, when I say circuit, what am I talking about? Am I talking about the circuits that you guys used in 2.11? No. The FPGAs that we use in this class are small FPGAs, but they have a capacity of 115,000 logic gates. 6 input logic gates? I think there's 6 input LUTs. 5 or 6, I can't remember. James, can you look up how many inputs the LUTs have on a Cyclone 4? Yes. I think there are 5 input. Anyway, 115,000 logic gates. Not only that, but they have multipliers, multiplier circuits on them that are used for arithmetic, and memories on them, as well as I/O pins that are also reconfigurable in and of themselves. And you might say, well, how do you reconfigure an I/O pin? Well, you can change its voltage. You can make it as a 2-volt pin or a 5-volt pin or a 3.3, 4 input. Okay, yeah, 4 input gates. So they have I/O pins that can be differential in multiple logic levels and that kind of stuff. Okay, you guys with me on that? Does that make sense? So it's like a blank slate, and you program it to become whatever hardware you need it to be. Now, how does that work? Well, it's based on, fundamentally, they're based on these things called LUTs, lookup tables. So if you guys remember from 2.11, you've got digital logic gates, and the different gates do different things. Like you have an AND gate and an OR gate and an XOR gate, right, inverter, and they all have some Boolean function associated with them. In an FPGA, you have these things called LUTs, which allow you to make them whatever kind of gate you want them to be. They're flexible in that way. But fundamentally, what they are is they're actually a little memory. So what you do is you program that memory with the truth table of the gate you want to implement. You guys remember the truth tables, right? So you have a truth table in 2.11 that defines what the output of a gate is based on its inputs. And when you draw a truth table, you write down every possible combination of input values, right? Well, in a LUT, you just envision that truth table as being a memory, and instead of inputs, that's the address. So you just associate the inputs as an address, right, in the table, and then you just fill in the contents of that table with the truth table. So here's an example. This is a 3 LUT. So as James just mentioned, in the FPGAs that we use in class, they have 4 inputs. This is an example of a 3 input one. So this is a 3 input LUT. It's a small one. And you can see as a 3 input LUT, it has 8 rows, 2 to the 3rd power rows or entries. And by filling in the contents of those entries, which is kind of the output there, you can make any arbitrary 3 input gate. You can make it behave however you want. You just give it a truth table, use that truth table to fill in the memory, and then you've got a memory where the inputs now form the address bits into that memory, and the output will then behave as the truth table is supposed to behave, right? So it becomes a flexible logic gate, right? Make sense? Okay. Now, the other problem, though, is you've got these logic gates. How do you connect them together? So an FPGA is a sea of these LUTs. You can think of it as a sea of logic gates. And a sea, when I say sea, I mean it's a 2D grid, two-dimensional grid, has columns and rows. But you have to also have a way to be able to connect any one of those gates with any other of those gates. So I want to be able to take the output of any of those gates and connect it to the input of any of those gates, right? So I can form complex digital logic designs. That is accomplished using a programmable interconnect, or what sometimes people call a switch fabric. So the first thing you do is configure the LUTs by initializing their memories, the little tables. You set up the tables and the LUTs. That creates your own custom logic gates. And then you program these switch matrices between them to be able to route outputs from any of these to inputs of other ones. And that allows you to take an arbitrary digital logic circuit and place the gates in this grid and then route them, connect them using this programmable fabric, switch fabric. Does it make sense? So there's two pieces of reconfigurability on an FPGA. One is the LUTs, which is the actual logic that does the number crunching, right? The actual computation is done by the LUTs. But they also have to be connected into a topology that's defined by your circuit diagram. So you have this circuit, and you have an AND gate connected to 3 OR gates, so I have to make those connections, and those connections are made through these switch boxes. The switch boxes are basically just transmission gates, if you've heard of that. It's an electronic switch that you turn on or off, is really how those are made.
So it depends on like active high and active low, like the voltage of the switch boxes.
Well, yeah, so if the switch box is on, it'll short 2 wires together. And then if you want to form a route, you're going to have to say, all right, here's a wire going horizontally, and I'm going to short it to this first one going vertically. So that'll short this one to this one, and then now I have to go over this one. So now I'll short it to another horizontal one and come over here like this. So by forming shorts between where these wires cross in the grid, you can create arbitrary paths. They're basically Manhattan-style paths, where it's like on a city street, where you can go over, down, over, up, depending on which ones you connect. Right? There's like city blocks. Now, obviously, you want those paths to be as short as possible, because the shorter those paths are, the more clock rate you can get, the higher clock speed you can get, because the clock rate has to be adjusted so the signals can travel all the way through the longest of all the paths. Right? The weakest path, the longest path. And so if you've got connections path, you can create paths that go through the whole chip. But you wouldn't want to do that, because if you did that, you'd have a really slow clock, because it would take too long for the signals to propagate.
That would depend on the performance of the code too.
Right, exactly. Yeah, but see, now fortunately for us, you don't have to worry about that, because the tools, remember I mentioned that if you want to use the tools on your computer, it's a big download. It's a 25 gigabyte download. And you might say, why in the world would a CAD tool be bigger than a Blu-ray disc movie? Don't make sense. Where's all the data coming from? Why is it so big? It's big because the software is complex, and the size is actually from the technology libraries that support all the various FPGA parts that you can target. So every FPGA, and there's a lot of them, there's a lot of variations of FPGAs, different sizes and specs. But every one of those has to have a technology library that tells the compiler what the structure of this grid is. And this grid, there's lots of stuff in here. Like I mentioned, there's 115,000 logic elements on the FPGA we use in this class. But you can imagine how many of these switch boxes there must be, because the switch boxes have to account for every possible way to map. You have to account for every possible way that you could connect those 115,000 gates are encoded in the hardware design here, right? And then obviously you're only using a small subset when you actually implement the design. But the technology libraries have to have information about all of that. So that's why it's a big, cumbersome download. Okay, one other thing I want to mention is that there are more than just LUTs on an FPGA. There are also specialized memories called RAMs, on-chip RAMs that they put in there, and multipliers, and some FPGAs have PCI Express endpoints and memory controllers and other stuff in there. There's other stuff that's in this grid, but the LUTs are the things that comprise most of it. You'll have other things in there, but they're usually much more sparsely instanced inside the grid than the LUTs. The LUTs are like really the main part of the FPGA. And then you'll have a column here and a column there of maybe RAMs or multipliers. Okay, you guys with me? Okay. Oh, there's also phase lock loops, PLLs. A phase lock loop is also very important because in FPGA, I mentioned clock speed before. So, you'll have a design, you might want to make a design that runs only at 50 megahertz, or you may have a design that runs at 500 megahertz. FPGAs can do both depending on how complex your design is, right? The problem is that how do you change the clock speed? How does that work? That's done through these PLLs. So the boards that we have I think there's 3 crystal oscillators on here. The main one we use is a 50 megahertz oscillator, which is connected to a pin on the FPGA. You use these phase lock loops to take that 50 megahertz signal and clean it up and minimize its jitter if you want to do 50 megahertz. But if you want a faster or slower clock, the PLL is an analog circuit that allows you to adjust the speed, the clock rate, and the phase. And often, even in this class, we're going to be dealing with multiple clock domains. You guys with me? You might say, why? Because there's a memory, there's an off-chip RAM, like you have in your computer. You guys have a RAM, like any computer, your laptops, you have a RAM. That RAM runs at a slower clock rate than your CPU, much slower. Your CPU might run at like 3 gigahertz. The RAM's only running at 800 megahertz if you have DDR3, right? So it's like 3 or 4 times slower, right? Other peripherals on the FPGA may have other speeds, like once we introduce video, like when we create a video signal, the video signal needs to have a clock that controls the pixels on the screen, the individual pixels. Every pixel on your screen, like if you have a display, a monitor, you take the number of pixels on the monitor and you have to multiply that by the number of frames per second the monitor refreshes, right? And that's the clock speed. That's the pixel clock speed. It's the number of pixels times the frame rate. And so that's another clock speed. And when you have a system on chip where everything is on one chip, then obviously you have to deal with, you've got the memory, the video circuitry, and the CPU. You got 3 different clocks, and we'll have 3 different clocks that we'll have to deal with when we do the hardware design part of this class. You guys with me? Okay, skip over that. Okay, so one final thing I want to talk about FPGAs. This is just background information, just so you guys are on the same page. One of the things you're going to find in this class is when you compile hardware designs, when you design hardware and you want to compile it and have it run on an FPGA, it takes a long time. And also, you'll notice that as it's compiling, it's generating sometimes hundreds of messages to you. There's just messages and messages that scroll, lots and lots of stuff. It gives you all this information. Most of that stuff I can't even read. I don't know how to interpret it. There's all this information about timing and skew and all this stuff that scrolls by as you're compiling it. Sometimes you'll get a warning or an error in there as well that'll kill it. But there's lots of information. It's a really complicated process, and it's really hard to explain why it's complicated. Part of it has to do with this idea of mapping. So I mentioned that the LUTs in the case of this FPGA are 4 input, and I showed you an example of a 3 input one. One of the things you might be wondering is, well, what happens if I need what happens if I need a bigger LUT? What happens if I need a bigger lookup table, a bigger logic gate that has more inputs? right? It turns out that you oftentimes will need that. That comes up a lot. So how do you deal with that? Well, you have to go through this process called mapping, where you have to take a larger Boolean logic function and map it to smaller Boolean logic functions that'll fit into the physical resources on the FPGA. So an example of that is I have a really simplistic example, super simple. This is a full adder. It's a 1-bit adder, right? So you have A input, a B input, and a carry in input, and it generates a sum and a carry out. So it's just basically adding 3 bits together, right? So this is the truth table, and it's an 8-entry table because I have 3 inputs and there's 2 to the 3rd power entries in the table. Well, what happens if I have an FPGA that only has the capability of a 2-input logic function? How's that going to work? What do I do? Well, I have to map the 3-input LUT to 2 2-input LUTs, right? And there's a trade-off here because I can't fit that in, so I have to split it into 2 smaller ones, and obviously I'm going to have to convey some intermediate signal between them, and that's going to cause the latency of this thing to be higher because I got to go through more stuff between my inputs and outputs, right? The question is, how do you do that? Well, I tried it with this example, and it took me a while to figure it out. Basically, and this was just kind of trial and error, I used Boolean logic theorems from the ones that you should have learned in 211, and I tried to manipulate that expression. This is the one for just the sum, not the carry out. This is the sum. So basically it's an XOR, 3-input XOR. So I expanded the XOR out to ands and ors, sum of products, and then I transformed it a few times until I got it to the point where I could calculate S as a function of one of the inputs, in this case A, and another input that was an intermediate input that I could generate as a function of B and C, right? And like I said, I just randomly get, I don't know if I don't know how to, what methodology, what algorithm you follow to do this. I just kind of randomly tried this to make this work. It ends up giving you, that's kind of hard to read, but if you look at it as a truth table, you can see that this truth table is the original one. This one is, I'm just adding the S0 column. And you can see that S0 column repeats, 0, 1, 1, 0, 0, 1, 1, 0, which means that if you look at this truth table, the A input relative to the S0 output, A is a don't care, because that S repeats 0, 1, 1, 0 if A is 0, and 0, 1, 1, 0 if A is 1. So A is a don't care for the purpose of calculating S0. So that way I can break this into 2 smaller tables where I calculate S0 only as a function of B and carry in, right? Because again, S0 is a don't care for A. And then I can take A and S0 and calculate the final S value, right? As with a lot of Boolean algebra style stuff, that's NP complete to solve that. So in other words, if I gave you an arbitrary Boolean logic equation and I told you to break it into smaller equations, it could take a really long time to find that solution. And it may be the case that the solution doesn't exist. I think. But in any case, it's hard to do. And so that's part of what these tools have to do. Once you've got those 2 smaller tables, then you have to decide where you want to put them in the grid. This is called placement. So you have to place them. You have to take these logical tables and associate them with physical hardware inside the chip. Ideally, you want them close together, right? Then when you're done with that, you go to the switch matrix and you set up the switch matrix, the switch matrices, I should say, in the routing fabric to route the signal. Because remember, there was an intermediate signal, S0, that had to be routed between those 2 tables. So that gets routed into that reprogrammable fabric. And that's called routing. So you take your design, it has to be mapped, break it into smaller tables, then it has to be placed where you put them on the grid, then it has to be routed. You have to go through those 3 stages, and all of those, it takes time, even on a powerful workstation. You tend to have to wait much longer than as compared to compiling software. Yes.
Okay, mapping. You say you can use any other like method, like what's like by method you mean like K mapping or like?
Yeah, well, you could use K mapping to reduce it down, but at some point you're going to reduce the complexity down. You're still going to have too many inputs. So the point is to reduce the number of inputs. And so you have an expression with 3 inputs, but I can't map. I don't have any LUTs that are 3 inputs. So I want to break it into 2 smaller tables with just 2 inputs. One of those inputs will, in one case, and they'll be connected together. And that's even harder to do than minimization, at least conceptually. I don't know about computationally or not, but that's a different process. Yeah, we don't teach that, obviously. And the good news is we don't have to do it because the tools do this for you. The Cordis tools that we're going to use in this class are going to be doing that behind the scenes. But this is a way for me to explain why you're going to have to wait a while for that to happen because it's complicated. Okay, so the board that we're going to use, this is a TerraSig DE2 115. I use this board for both my classes, 611 and 313. It's nice. It works really well for both classes. And well, I don't use it for 611 anymore, but I used to use it for both classes. This board is nice because it's got a lot of stuff on it. I've never found another board with this much stuff. You might be thinking, well, why don't you just use like a Raspberry Pi or like an Arduino or something like that? None of those boards have all this stuff on it. This has more stuff than anything. When I say stuff, I mean it's got switches and buttons, 7-segment displays, LEDs. It has multiple memories. It has flash memory, SRAM, DRAM. It's got an SD card slot. It has GPIO. It has serial, 2 Ethernets, VGA, has an audio chipset. It has 3 USB connectors, host, a device, and a reconfiguration. It has JTAG. It has an LCD screen. It's got, it's built really well. It's durable. It's got like a plexiglass. I don't know if you can see that from the back, but it's got like a plexiglass thing that protects it. So, when frustrated students throw it, it tends to hold up for a while. I mean, we've lost some. It's not indestructible, but it is a heck of a lot more durable than a Raspberry Pi would be. It's built to be used in a classroom setting. And the best part about this, even better than anything else, they've been continuously selling and making this board for like 15 years. So the greatest thing about this is, like, if I had bought a BeagleBone Black from Texas Instruments like 3 years ago, I would have to redesign the course for a new board because they don't sell it anymore. They discontinue those things. This thing has longevity from this supplier. Now it's getting a little old. It has kind of an old, the Cyclone 4 is kind of getting a little old in terms of FPGA technology. But it's great because we can continue to refine the course. I can make the course better without having to redesign it from scratch for a whole new platform and start from scratch every couple years, right? So this way, you'll notice, now things aren't going to be perfect in here. There's going to be frustrating bugs and problems that you encounter that I even can't solve for a while. Oftentimes, there'll be a problem that you guys will encounter that will take me the whole lab, the whole class, just to figure out one group's problems, because there's a lot of things that can go wrong when you design hardware and software on bare metal. But you'll find that things are the actual projects and the tooling is pretty polished. And we wouldn't have been able to do that without a company that kept producing the same board for a while. Okay, so let's switch gears here a little bit. Let's talk about the OnChip Interconnect and how software talks to hardware. So when I was in undergraduate school, I was always interested in how hardware and software communicate. You guys ever wonder about that? You might know a little bit about that already. You learn how to write software, and you can write software that writes text to a terminal and accepts keyboard entry and mouse and that kind of stuff. But how does the software talk to those those devices, those peripherals. And I used to know, like, just vaguely, like, oh, there's a driver. There's a device driver in the operating system that takes care of that. But I never knew how the device driver works. Like, what does a device driver do? What is happening there? How does a CPU physically talk to hardware? How does that work? Well, it turns out that you guys already learned how it works indirectly in architecture. When you guys took 212, computer architecture, you learned about load and store instructions, right? But you were told that load and store instructions are designed to read and write memory, right? The RAM. Well, it turns out that you also use load and store instructions to write to I/O devices as well, to hardware. The only difference is that you have special memory address ranges that are called I/O mapped, I/O ranges. And if you write or read using a load or store, sorry, I should say write or read using a store or load, to those special address ranges, those ranges map to hardware instead of memory. So what I'm saying is that ultimately when you write a device driver, you're really just doing loads and stores to special memory ranges. Now, you can't do that if you have an operating system, because the operating system will stop you from doing that. The operating system won't let you directly communicate with hardware. You have to go through the operating system services. But if you're writing bare metal code, like we are in this class, and like just about every embedded system does, you get to write your own device drivers. Now, there's some built-in code for you that are kind of like drivers that help you out and there's a hardware abstraction layer. But there's no memory protection in an embedded bare metal system. There's no memory management unit, and there's nothing to stop you from writing or reading any address your user code wants to write. Nothing will stop you. So your code has complete control of the system. You can talk to all the hardware you want. No one will crash you. No one's there to stop you. You guys with me? And we'll be doing a little bit of that. So for instance, I want to light up a light. I want to write code that lights up a light on the board. How do I do it? I do a store instruction to whatever address corresponds to that light, and I store a 1. And if I store 1, it turns off. If I store 0, it turns on. If I store a 1, it turns on. And if I store 0, it turns off, for instance. You guys with me? So I can light up lights by just storing 1s and 0s to special addresses. That's basically how it works. Now things get more complicated when you want to do, like, say, Ethernet. When you want to do networking, because with networking, there's a chipset for the network adapter, and you're not directly writing stuff that goes out on the network. You're writing instructions to the network interface card, and the network interface card is doing some translation for you and communicating with the network on your behalf. So that stuff gets a little bit more complicated. Likewise with sound. Like if you want to do audio, you have to write stuff to the audio chipset, and then the audio chipset will, you write instructions to it with store instructions. You give it a frequency and a phase and tell it to go, and then it'll play that tone, for instance. So, but generally speaking, that's how you do it. Now, if we look at the processor, a typical processor has 2 memory interfaces. There's usually an instruction interface that you connect for reading and writing, well, not writing, but reading instructions, because that's usually read-only, right? And then there's a data interface where takes care of the memory and the I/O. Now, some embedded processors have 2 data ports, one for memory and one for I/O devices. But in this class, we're using a processor called the Neos 2 processor, and it only has 1. You guys with me? So what I'm saying is that you have a processor, and I'm going to attach the instruction interface, the instruction master, to a memory that has my code, my program in it. And then I'm going to take the data master and connect it to not only my main system data memory, but also my peripherals, my lights, my USB adapter, all my I/O devices. And that way, when I do a load or store, it'll go out through this interface. If I fetch an instruction, it goes out through this interface. You guys with me? So you have to connect. You're going to have to connect when you start your project. You're going to have to create a processor And then you're going to have to connect its memory interface and its data interface to different things depending on what you want them to be connected to. And those connections are going to be made through the Avalon bus, which is the on-chip network, the on-chip interconnect. You guys with me? Make sense? So my point here is that this is a fairly standard interface. This is basically just, if I want to write, I put data out and I give it an address and I tell it to write. And if I want to read, I give it an address and I tell it to read, and then I'm going to expect something to come in. And that's it. And that's how I communicate with memory and with all of my I/O devices. Right. Okay, and then when you create your system, you will be creating you'll start out with just a blank slate. First thing you'll add usually is your CPU, and then you'll start adding peripherals. Every peripheral, most peripherals are slaves to the CPU. Every slave is going to have a range of memory addresses. Those ranges are all non-overlapping. They're all separate from one another. They all cover different ranges of a 32-bit number. So you have a 32-bit number, which represents your memory space. And then you'll have start and end segments of that. You'll split that up into segments, each one of those segments corresponding to a specific memory or a peripheral. So for instance, this is a memory map. So I've got address 0 at the top, and I have address 8Fs at the bottom, which is 4.2 billion or so, right? And then of that range, I can split it into ranges. Each range is a start and end address. And that start and end address for I2C is this, for UART is that. UART is for your text console, by the way. Stands for Universal Asynchronous Receiver Transmitter. You guys with me? Now with an FPGA, you can change that. So as you add peripherals, you get to change those ranges, but it's easier just to let the software do it automatically. So there's a button you can hit where the software will automatically set those ranges. So you'll add stuff, you'll add peripherals. Sometimes you'll add one and it'll say, oh, there's an address conflict. Well, to resolve that, it's simple. You just say remap addresses, and it will divide up the memory address space for you. Right? Now, obviously, it's possible to have too many things in there and not enough addresses, but I've never seen that happen. Usually, the biggest chunks of that are taken up by the memory. Peripherals usually don't take a very wide range. Like, for example, notice this here, I2C. It starts at A and 7 zeros, and it ends at A and FFFF. So that means that there's 65,536 bytes. There's 64K in that range. That's not much. Actually, that's more than I would expect that to have. Everyone with me? Okay, so these are things that you're going to need to understand as you assemble your embedded system. Okay, so let's talk a few specifics here. So we'll be using 3 different pieces of software. First of all, let me give you a little bit of background. The FPGA we're using is a Cyclone 4. Like I said, it's getting kind of old. I think they came out in probably 2006, something like that, somewhere around there. It's kind of old. They still make them though, and they're more than good enough for what we do in this class. But they were originally made by a company called Altera. Altera was recently purchased by Intel. Intel realized that they are going to need FPGAs, so they bought the whole company of Altera for billions of dollars. Soon after they did that, they started expunging the word Altera from websites, documentation, software, comments in code, everywhere. Intel started systematically eradicating the word Altera because that was the name of the company that made these FPGAs before Intel bought them. So there's a little bit of confusion. when you download the tools and when you open the tools, you're going to see Intel FPGA. Sometimes, though, you're going to see an Altera FPGA, or you'll hear me say Altera, because I still call them Altera FPGAs, because I haven't gotten used to calling them Intel FPGAs yet. That's where that comes from. There's another big company that makes FPGAs called Xilinx, and they've always those two were always competing with one another. Maybe someone will buy Xilinx one day, but so far Xilinx is still by itself, and Altera is now owned by Intel. So we're using Intel FPGAs technically. The software, the main piece of software that we're going to use is called Quartus. Quartus is sort of the starting point of all this stuff. So you start up Quartus. Quartus is where your hardware synthesis tools are. So Quartus takes your hardware design, just your hardware, and it converts it into a bit stream. So it goes through that process I was describing of map and place and route, right? And that's slow. That's the one that I was telling you has all the little warning messages and stuff that scroll by and you don't know what it means. That's Quartus. So Quartus is used for compiling the hardware. There's another tool that you access from within Quartus, but it's actually a separate program. It comes up in a separate window that runs in parallel with Quartus. It's called Platform Designer. This used to be called SOPC Builder until recently they changed the name of, it went from SOPC Builder to QSys, and now it's called, Intel decided they want to call it Platform Designer. Platform Designer is a way that you can build a platform, and a platform is a sort of a system with a processor and peripherals connected with an Avalon bus. So it's kind of a very abstract hardware design tool where you say, I want this CPU with these features, and I want these peripherals, and I want to put them all into this system, this embedded system. So in other words, you're creating an embedded system with this Platform Designer. It's an embedded, multi-processor reconfigurable system on chip architecture, right? So you put all this stuff together with with Platform Designer, and when you're done, you save it, and it will generate the hardware for you, the underlying hardware that makes that system, some of which is encrypted because they have to protect some stuff. The design of the CPU, for instance, is an encrypted hardware design. But then you run that through Quartus, and Quartus will synthesize that hardware into a form that you can use to program our FPGA or any other FPGA, any other Intel FPGA. You guys with me? It'll also tell you like how fast you can run the clock and that sort of stuff. You guys with me? So these are two separate tools. Usually you'll have them both open at the same time on your workstation. Now, prior to this semester, this is something we're changing. We used to use a third tool that was the tool that you use to write the software for the processor. So when you run Platform Designer, you create an embedded system that includes a processor, right? But that processor needs to be programmed like any other processor with C code or C++ code, right? So we used to have a third tool that was a variant of Eclipse. Same Eclipse that you use in 145, 146. And it was, we used that to compile the C code and then take the compiled C code and send it into the FPGA onto the configured FPGA, right? So basically you start out with a blank FPGA, you put a processor on it by configuring the FPGA, then you program that processor. And we did that with Eclipse. But Eclipse is horrible. It's really bad. You guys probably experienced some of this when you took 145, 146. But it's much worse in this class because Eclipse has a lot of stuff it's got to do. It has to talk to the board, right? Like when you compile code, it has to be cross-compiled for NEOS, right? Meaning that it won't run on Intel. Like if you compile your code and you try to run it on your Intel machine, it'll just say like, what? What is this? I don't get it. I don't understand. What is this? Because it's only, the code is native machine code for the NEOS processor, right? So you cross-compile the code. But see, Eclipse had this thing where it would compile it into the code, and then it would download it to the FPGA, and then it would run it, And then the console, whatever you printed, would come back on the opposite way through the connection back to Eclipse. The problem is it never worked really well, because sometimes you'd go to run your code and it would just hang, and it was really clunky, basically. And the biggest problem with it is when it failed, it would never give you any feedback. Like, you would hit run and it just wouldn't work. And it was like, well, what's the problem? Did I not configure the FPGA? Do I not have it plugged in? Did I not power on the board? What is the deal? Like, did I have a switch wrong? So we decided, starting this semester, this is a new thing, we're going to switch from using Eclipse, we're going to use the command line tools. We're just going to use text like you did in 240. Guys, you did this in 240, you had make files, and you basically just used text editors and just a Linux prompt to build your software. And so we're just going to use that along with some command line tools that allow you to deploy your code on the FPGA. To be honest, I don't have a huge amount of experience with the command line tools. I've always used Eclipse myself, but we have a couple research projects that we're doing in the lab. And I've got some students that have been working on this, and they've worked out all the details of doing this command line stuff. So it seems like it should be better than Eclipse, but worst case scenario is it doesn't work out well, we can always switch back to using Eclipse. Any questions about that? Okay, so bottom line is you have three tools. You're going to have a window for Quartus open, you're going to have a window for Platform Designer open, and you're going to have your command line tools open in a terminal. And all three of these are needed to do what you need to do. You're going to have the Platform Designer that makes the hardware, Quartus compiles the hardware and programs the FPGA, and then you're going to use your command line tools to run your software on your CPU. Now you might be thinking, wait a second, this sounds unnecessarily complex, that we have to go through all these steps. And that may be true, but this is designed to mirror the process that all embedded systems companies go through now when they make a chip. When Apple comes out with a new iPhone, this is exactly what they have to do. They have to start with the hardware design. They design a whole new chip for every iPhone. You know, they start out with the i5, or the A5, the 6, the 7, the 8, the 9, the 10. Now they have the A11 Bionic, right? They have to update the hardware, so they come up with a new system on chip, and then once they have the hardware, then they write the software to target that specific hardware, right? I'm talking about the low-level software, obviously. The apps and stuff is common, but the drivers and the stuff that make the emojis work, the animojis work, and the studio photography, the computational photography stuff, all that is written to interface with the low-level hardware components that they put in the new version of the chip. The new vision processor, the new GPU, all that stuff has to be rewritten, all the low-level stuff. And it turns out that Samsung does this and all these codes. So what I'm trying to say is that embedded system design in this day and age is a hardware software co-development where you design the new chip and then you design the software for the chip. And these tools allow us to do that. We're just doing it on an FPGA instead of making an ASIC like Apple would do. An ASIC being a custom silicon chip as opposed to a reprogrammable chip. You guys with me? By the way, I mentioned earlier that FPGAs are in a lot of devices that we use, like in your car, elevators, all over the place. You might say, well, wait a minute, why would they use an FPGA in a car? Why wouldn't they just make a chip? Well, FPGAs are most commonly used. We're using them for teaching. But FPGAs are designed originally, primarily, as glue logic. So anytime you have a system in any complex electronic device that needs to talk to another component, they usually have to go through an FPGA that serves as kind of a intermediary. It translates two languages. They're used to convey information from one place to another. So in a car, you have the radio will get louder if you speed up. Well, the radio has to talk to the system that records the speed, and that's generally going to be done through an FPGA. Now that's starting to not be so true anymore because there's a lot of standardized buses that the industry they're standardizing they have the CAN, the controller area network. So there's some standardization which has lessened the reliance on FPGAs, but they're always been used for glue logic. Okay, anyway, moving on. Let's see, how much time do we have left here? We go till 25 after? No. 35 after, good, okay. Okay, so platform designer. So I'm gonna, I only have I've got about 20 minutes, which is not gonna be too much time, but I just wanna sort of show you how you get started in case you're interested in getting an early start in the lab. So the first thing is that I have a script that I wrote that is in a shared network, a shared network volume directory. It's available on all the lab machines. User local third-party CAD setup files. It's a long directory, but then there's a thing called altera.bash file. You have to run that file, and that will set up your environment to use the tools. When I say environment, I mean path, license server, and a couple other variables that tell the tools where they live in the file system. I'm hoping you guys should know from 2.15 that you can add that line source and the path. You can add that to your .bashrc file, and it'll run automatically. You might be uncomfortable with running that script and not knowing what's in it or whatever. You're more than welcome to open that file and copy its contents to your bashrc file if you're more comfortable with doing that. I don't care, but it's just a basic setup script. Once you do that, you can start the tools by just typing Quartus and hitting enter on the prompt. Now you might be saying, wait a minute, isn't there like an icon or something we can just double click on the desktop or a start menu or something like that? No, you have to actually open a terminal and type Quartus. I don't know how to add this to your start menu in Linux. Never figured that out. I don't think I can because it would have to be probably rolled out by Ryan to all your accounts, which I don't have the ability to do. Okay, you guys with me so far? Yes?
So if we wanted Quartus on our computer and all, we had to do the same thing, same SSE?
No, you can do it over SSH. Yeah, so you have two choices. If you want to run this on your machine, you can SSH in, and you can, if you're on Windows, you can use, there's a program called MOBA Xterm, and if you're on Linux or Mac OS, you just have to, I think you can just SSH with --Y and tunnel X connections. And once you got that, then you just connect any of the lab computers, like L-1D43-01-CSCE.sc.edu, port 222. You would just connect, and then you could run that, and you'll get Quartus on your own machine.
Okay, so we don't have to physically download our own.
Well, there's a trade-off. So if you do it this way, where you remotely do it, it's going to be slow. It's going to be clunky and slow. And also, you will never be able to program the FPGA because you have to run the tools locally if you want to actually program the FPGA from your computer. So you could do it that way, but you give up some stuff. If you want to program an FPGA by connecting it to your machine, which there's really no point because we have to keep them in the lab anyway. But if you wanted to do that, or if you wanted a faster interface, then you could download it from you just go to Google and search download Quartus, and I think you might have to create an account on their site, but you can download it, and there's a free version you can download. The free version supports our chip, the Cyclone 4. So we use the full version and we have a license, but the free version will work. Okay, so that's it. Let's see here. I've got, so just to show you how to do that, if I type source, user local third party, this is a terminal to this is actually one of my lab machines. Let me, I'll show you. I'll SSH to L-1D43-01.csc.sc.edu, port 222. And then log in, and then I'm in. Okay, so I'm connected, and then I can type source, user, local, third-party CAD setup files, altera.bash, and it's set up, right? Once I've got that, I can just type Quartus, and I'm on Wi-Fi. This will probably be pretty clunky. So instead of running it off there remotely, I'm going to just go into my local machine here in Cygwin and just run it from here. See, that was much faster. Okay, so I ran it, and this is what you see. So this is a little overwhelming at first because there's a lot of stuff here, but you'll get used to it. It's kind of empty right now because we don't have a project started. So let's start a project up. So we'll do File, New, and we'll say New Quartus Prime Project. And let's see if I can. I'm going to browse. So the working directory. See, the other one just came up. See how slow that took? The one I launched remotely just came up now. So this is the one I'm running remotely. You can see though that it looks identical. So this is the version from Linux, and this is the version from the Windows native. They're both, by the way, just so you guys know, they're both identical because they're both written in Java. Both versions are written in Java. So they're literally the identical code, whether you're on Linux or Windows. All right, so I'm using Windows, but it makes no difference visually. Okay, so the colors are a little different. You can tell the Windows version is a little lighter colored, but aside from that, they're the same. All right, so I'm going to create a new project, and let's see. I'm going to put it on a directory I can access from my Linux machine as well. So it's on the Z drive, Data, Designs, Lights. So we're going to call this project, well, you can call it whatever you want. Historically, we always called it Lights because the first example that you set up is just lights up some lights on the board. That's why we call it Lights. It's not really that important what you call it. Okay, so it says you want to create the directory, it's empty project. I'm not adding any files because I'm going to create the files once I have the project created. Now this is the part that's a little frustrating. Remember I mentioned that there's lots of FPGAs? This is how you find out about that. This thing is asking you to choose your FPGA. The easiest way to do that is to try to narrow it down. So we're going to have a Cyclone 4. I think when you do this in the lab, there's going to be more options here. But I'm going to say Cyclone 4E. The package is FPGA. Package refers to the actual ceramic package they put the chip in. You know, the little thing that you see on the circuit board, right? FPGA stands for Flip Chip Ball Grid Array. Pin count is 780. And the speed grade is, oh gosh, what's the speed grade? 7, right? 7, I thought so. Yeah, 7. 7 is the speed grade. Now once you do that, you'll still have some options down here that you have to choose from. The one we want is this one here, the EP4CE115F29C7. That's a long name, but you'll see if you're in doubt, pick up a board and just read that number off the chip. This board, the biggest chip on this board is the FPGA, and it's printed right on there, right? So that's the actual device type that we're using. And once you get past that, you can just hit finish because it's asking some other questions here, but we can just bail at that point. All right, so we go through the obligatory spinning here for a while. Okay, so it creates the project. And let's see, what did I have next on here? Now, also, just for your reference, too, I have in the lecture slide, you can download these lecture slides from Dropbox, and they sort of outline this process, but they're a little vague. But remember, I'm also recording this, so you'll be able to go to YouTube and be able to see me walk through this as well. Okay, so once we get into our, the device name, by the way, is on the slides there too. Okay, the first thing we want to do is go to Tools. Oops, that's the wrong Quartus. That's the Linux one. Let's go to Windows. Okay, we go to Quartus here, and we'll go to Tools, Platform Designer. And we can start that up. So this is that second tool I was telling you about. And we'll come back to Quartus. I'll point out what the different parts of that window are. Okay, so the first thing you see over here is this is actually a simpler interface than Quartus. This just has this big area in the middle represents your system, your platform, your embedded system. There's a little place for messages down here. There's this, which is, I guess shows, I don't know actually what this stuff is. I never really looked at that pane very closely. But that thing up there is the IP catalog. So the way even Apple designs these chips is they design the system. They take a chip, they design the chip, and they decide what they want to put on the chip. But the things they're putting on were designed by other people, except for the CPU. I think Apple designed the CPU in-house. But generally speaking, you go out and you purchase IP from third-party companies that are called fabless IP design companies. So there's lots of companies out there that design hardware, but they don't actually make a chip. They just make the design. Then they sell it to a company like Apple or any other company, Samsung or Qualcomm, who buy that design and they incorporate it into their larger system on chip, into their bigger chip. You guys with me? Makes sense, right? I mean, you guys probably heard that like the iPhone chip has like 10 billion transistors on it, right? I mean, you've got to imagine that Apple is not designing a chip with 10 billion transistors. That would take an astronomical, think about how hard that would be for even a big company like that. A lot of these things are pre-made designs that you incorporate, and those are called IP. IP stands for intellectual property, which I never quite understood why that term is used to describe pre-made hardware designs, but that's what it's called, and that's what that means when it says IP catalog up there. All right. So anyway, the problem with this though is there's so many options we have that it's really hard to navigate this. So you pretty much have to add everything through searching. Let me just show you an example. So we can go here to memory interfaces and controllers, flash. We can do a flash interface. We could do a DDR2 SDRAM controller, an SDRAM controller. Some of these are grayed out because I don't know why those are grayed out. I guess I don't have the right chip selected or something. I guess they're not compatible with the Cyclone 4. Processors and peripherals, we've got coprocessors. Got custom instructions we can add to the NEOS. There's embedded processors, hard processor components, trace IP. A lot of these are grayed out. Mailbox, mutex, interrupt latency counter, MSI to GIC generator. Then we've got this university program down here. The university program has a lot of components we're going to use because Altera, before they got bought by Intel, designed a lot of IP components that are designed specifically to talk to the components on this board and the other similar DE boards. You guys with me? So we're going to use a lot of stuff from there, but you don't have to hunt from it. You just have to search. Right here, there's a search bar. So the first thing we're going to add, let's see, what's the first thing I got here to add? Processor. So we're going to add a NEOS processor. So if you just search for NEOS up here in the search bar, you can find the NEOS 2 processor down here. Just scroll down to find it. Now you guys double click on it and it'll add it to my system. Now you might be wondering what the NEOS processor is. What's the deal with that? The NEOS is, you can make your own processor, by the way, and put it on this FPGA. In fact, that's what we used to do in 611, my other class. But the NEOS processor is a pre-made processor that Altera lets you use for free. Why do they call it NEOS? I have no idea. I don't know what that means or where that came from. It's a weird name. But I can tell you that it is basically it's a MIPS processor. You guys know MIPS from 212? If you look at the instruction set of NEOS and the way the instructions are encoded, it looks very, very, very similar. Now, it's not exactly the same, but if I were to show you assembly code from NEOS, you guys would all instantly recognize it. You could all read the assembly language code for the NEOS because it's exactly like the MIPS that you guys learned about in 212. So that's good, right? once I add the Neos, it gives me some options here. I can choose between two versions of the processor. There's the Neos Economy and the Neos Fast. The Economy is smaller. It uses less FPGA resources. So I could fit, for example, I could fit more of them on there, right? But the Fast is faster, but it's bigger, it's heavier weight, and it uses more of the FPGA. So, but in this class, we always use the Fast. And there's some other options in here. I can configure the cache size. I can configure whether it has a divider on it, a hardware divider. You can actually even add an MMU, a memory management unit, which I've never tried to do. That would be if I want to run an operating system on this thing, which we're not going to do in this class. But in theory, you could run Linux on this. Linux requires an MMU, or you can't run Linux. But we're not going to use it. JTAG, debug, and there's a bunch of other stuff in here, a lot of which I don't even know what it is or haven't tried it. For now, we're just going to accept the default settings and hit finish. Okay, now this part is super important that you understand what happens next here, because it's a little bit unintuitive too. You'll notice that I've got two things now. I've got this thing called clock 0, and I've got this thing called, if I change these columns, what the hell is that? Oh yeah, Neos 2 Gen 2. This is the Generation 2 version of the Neos. That's redundant, isn't it? Why didn't they just call it Neos 3? I don't know. I don't know. It should have just been Neos. Like they had a Neos 2, and then a Neos 2 Generation 2. This is the generation, so this is a newer Neos than we used in the past in this class. Anyway, look at all the stuff it put in. Now, first of all, what the heck? I get Neos 2 because I just added that, but what's that clock thing up there? The clock is something they added new to this tool, and I find it a little strange. But what it is it's needed whenever you have a clock come into your system from outside the system. Remember I said there's a crystal on that board? There's a crystal on the board. The crystal sends a square wave, a 50 megahertz square wave into the FPGA. That signal's got to come into this design, and anytime you have a clock come in, you have to add one of these clock 0 things. It's just a bypass. It's literally just an entry point for the clock. It doesn't do anything other than that, right? Likewise, if you want to send a clock outside the chip, you also need one of these clock things. So we're going to actually have to add another one of these for our memory. We have a RAM, a DRAM we have to use. We have an external memory, and we need to send a clock to that. So we're going to have to add another one of these later on in order to send a clock outside. So if we're bringing a clock in, we need this thing. It's just called clock source. You guys with me? So I've got the clock source and I got the Neos. Now, as you might imagine, the first thing I got to do is I got to connect the clock to the CPU. I got to give my CPU a heartbeat, clock. So I got to make that connection. And once I do that, the next thing I got to do is I need a memory. The CPU is useless without a memory that I can use to put the program in that it's going to run, right? A CPU without a memory it can't possibly work because you need to be able to put your program in a memory that the CPU can read. So every time you have a CPU, you need to have at least one memory for it to run the program out of. So we're going to have to connect that to a memory, which I haven't added yet. So what about the clock? How do we connect the clock? Now here's the part that's kind of confusing. Notice I have a clock input and I have a clock output. The clock input's going to come from outside the chip. The clock output's going to go into my Neos, and it's going to connect to just about everything else on this thing too. Make sense? So how do I well, actually, you know what? I'm getting ahead of myself here. We need to add a clock manager first. That is remember I mentioned the PLL that allows you the phase lock loop? We got to add that first. So let me add that first. PLL, I'm going to search for PLL, and then I'm going to add Alt PLL, is that the right one? Oh, sorry. I'm going to add the university program clock, system and SDRAM clocks. So I'm going to add that. I'm going to tell it it's the DE2115. It's a 50 megahertz. And now I've got enough stuff to start connecting. Connecting stuff in here is all done through, you see all this stuff over here. The connections are made by clicking little bubbles inside this connection matrix. You guys with me? By default, every time you add something, it's not connected to anything. This is different from the old software we used to use in this class. We had a software before where every time you added something, it would try to automatically connect. But in this new platform design, this is the latest version of these tools, they force you to make all the connections manually. The only one they made in this case was the data and the instruction master to the JTAG debug, because those are done, that's a special thing that's done internally. But all the inter-component connections have to be established by you. You guys make sense? Okay, so that's why I have to go through this tutorial before we start work in the lab. Now, just to give you a little bit of a heads up, you're not going to have to do too much of this stuff, because once you set up your system in here, you're going to keep using that system the whole semester. You're just going to be making tweaks to it. You're going to be modifying it and augmenting it and adding capabilities to your system. But in this first lecture, we're going to set up a base system that you're going to build from scratch, but you're going to let it ride all the way through the semester. Okay, you're going to keep using it, you're going to reuse it for every project. So it's going to be a little bit tricky to get things set up initially, but once we get it set up, then we're going to switch over and be writing a lot of C code for it. Okay? All right, good. I will see you guys in 2 weeks, and if you want to come to lab, you're welcome to, but we're not going to be doing anything yet because I haven't assigned the first project yet. Although the first project is on Dropbox if you're interested in looking at it. Okay? All right, thank you.